Find the directional derivative of function f at the given point in the direction of vector v. This function is f of x, y, z, so this will be a four-dimensional because x, y, and z are all independent variable, equals to xy squared times inverse tangent of z. This thing can be set to equals to another dependent variable, usually we call that a w. And then this point is clearly in the domain of the function, and then the vector, we are moving to this direction. Okay, let's do the partial derivative, right? Because directional derivative, we have three independent variables. You have to do one with respect to x, one for y, one for z. So the derivative with respect to x, what is that equal to? That one only x is a variable, so that means the y squared, the derivative of x is equals to 1, so y squared, and then the inverse tangent stays. And then the partial derivative with respect to y, that is a 2xy, right? You bring the 2 down, and then the x and the tangent stays. The derivative of tangent, inverse tangent, so the xy squared stays. The derivative of inverse tangent z, that will be 1 over 1 plus the square of what is inside the parenthesis, which is a z square. Okay, we got it, and then we write the gradient. Okay, for this four-dimensional, we do this. This is called gradient. It's called del, del, del f of x, y, z. I usually call this the gradient of f. Instead calling del f, I would just say the gradient of the function, gradient of f, x of y, z, equals to, we put it in this form. So 1 for x, y squared, and then inverse tangent z, comma, and then 2xy. We just write the derivatives like that. And then comma, xy squared divided by 1 plus z squared. Okay, and then what about at that point? And then at point 1, 1, 1, right? So the gradient of f, x, y, z are all equals to 1. So at point, oh, it's actually at point 2, 1, 1, 2, 1, 1, 2, 1, 1. Okay, let's do a plug-in. So this will be a 1 square times inverse tangent of 1, and then 2 times 2 times 1, and then inverse tangent of 1, and then xy, that will be a 2 times 1 square divided by 1 plus 1 square. Okay, so, and then we have gradient at that point. So, and then the gradient at this point is equal to 1 is 1, inverse tangent of 1, so tangent of pi over 4 is equals to 1. And then 2 times 2 is 4, so that will be 4 times pi over 4, which is equals to pi. And then the last one is 2 divided by 2, which is equals to 1. And then what is next? The next step is we have to make the vector v become a unit vector u. And then the next step, let's switch to a different color, shall we? And then the next step is we have to make vector v is given, become a unit vector u. A unit vector u. Alright, so the way we do it is whatever v equals to, so just like a number, so let's say I give you a number 4. How do you make 4 equals to 1? You simply divide it by 4. That is equals to 1. So this is a vector u equals to vector v divided by its magnitude. So that will be a 1, 1, 1, 1, 1, 1 divided by the square root of 1 square plus 1 square plus 1 square, right? Okay, that will be the square root of 3. I will just keep this outside, and then times 1, 1, 1. I will just keep it like that. And then now we do the directional of vector u of that function. So that will be the directional vector. Okay, let's switch to a different color. So the directional derivative of vector u of this function f of x, y, and z. So there will be a dot product then that is equals to the gradient. Oh, this is called let me finish this first. The function, the gradient of function f at the given point, and then a dot product the unit vector. This is a dot product, not multiply. This is the alternative. This is called the alternative form of directional derivative of f in the direction of unit vector u. So let's go over this again. This is called the alternative form of directional derivative of function f in the direction of unit vector u. It's a pretty long name. In case you didn't catch it, let me repeat that one more time. Alternative form of directional derivative of function f in the direction of unit vector u. All right, so let's keep going. So what we have to do is we have to put the pi over 4 down, right? Would you prefer color code like that? So that will be a pi over 4, a pi, and then a 1. Do you prefer that? And then you multiply. So you multiply the unit vector u. So that will be a 1 over root 3, and then a 1, 1, 1, and then a 1, 1, 1. So basically we divide this into like 3 major stages, right? The first major stage is in blue. So we got to this gradient, and then we do a unit vector, and then we dot product the result. How do we do a dot product? So to do a dot product, you have to take this times that. No. Assuming you take the 1 over root 3 times 1, and then you just take this number, you multiply the product, and then you take this number, you multiply 1, and then you take this component, you multiply the last one. All right, so the first one, I can just take the 1 over root 3 out, and then we do the multiplication right here. So this will be pi over 4 times 1, and then plus pi times 1, and then plus 1 times 1. That will be a multiplication, and then don't forget the dot product of two vector is a scalar. So that is a 1 over root 3, and then we have a pi over 4 plus pi, and then plus 1, and then this is a scalar. Don't forget the dot product of two vector is a scalar. The dot product of two vectors is a scalar. So at the end of the day, I have 1 over root 3. So let's put it right here because I want to draw a description. So that is 1 over root 3, and then multiply a scalar. 1 plus 4 is 5 pi. So that will be a 5 pi over 4 plus 1. And then this is the final answer. Okay, let's go over this one more time. We started with a point, right? So 2, 1, 1. So I'm going to go over this one more time. So we say the point, the given point, x equals to 2, y equals to 1, z equals to 1 is in the domain of the function. Is in the domain of the function f, and then f of 2, 1, 1, and then you plug it into the function. That will be a x, right, times 1 square, and then times inverse tangent of 1. So that will be a 2 times pi over 4 equals to pi over 2. So now we have a point that is called x, y, z, and then the dependent variable w. We have one of each coordinate, 2, 1, 1, and then a pi over 2. This is a point on the surface of f. Is a point on the surface of the function. And then the slope of the function at that point, the slope, we can just continue right there, right? The slope of the function at that point traveling to the direction of the vector is 1 over root 3 times 5 pi over 4 plus 1. Vector v is 5 pi over 4 because you have a point on the surface, and then you are traveling to a specific direction. Because it's in a 4-dimensional, you have to give me a direction. Back to a single variable calculus, you have an xy plane, you don't need to tell me the direction, but now you do. So if you are going to that specific direction according to the given vector, then you have that specific direction has a slope. If you are going to a different direction, then that will be a different slope. Okay, so that is the end of this problem. If you like the way I explain gradient and directional derivative, give this video a thumbs up, subscribe to my channel for more contents like that. As always, I will meet you all in the next video. Signing out.